Hello everyone, myself Ravi Kumar KS. I am working as Assistant Professor in the Department of Mechanical Engineering, Maharaja Institute of Technology, Mysore. So, in this semester I will be handling Engineering Graphics. The subject is Engineering Graphics. The subject code is 18EGDL15/25. So, if you are studying this subject in the first semester, it will be 1.5. If you are studying this subject in the second semester, it will be 2.5. And the credits allotted for this subject is 3. Then CIE is the class internal evaluation or continuous internal evaluation is 40. Then semester end examination 60. This is the weightage of the marks in the exam. So coming to module 2. So module 1, my esteemed colleague Professor Yogesh Kumar KJ has taken the module 1 where he has discussed about introduction to the CAD subject or engineering drawing. Module 2 is orthographic projections of points, straight line and planes. So in the previous session, one more colleague, my esteemed colleague Professor B. Harish has taken the projections of points in the previous session. So in this session, I will be dealing with projections of straight line, orthographic projections of straight line. So today's topic is orthographic projections of straight lines. The difference between points and line. A point is dimensionless. Okay, it is having only the coordinates, the distance from x and distance from y. But a line is the shortest distance between 2 points. Okay. Say for example, this is a line A and B. The distance between A and B is called as a line. It is one dimensional one. Then in the case of points, you will be dealing with all the 4 quadrants. That means to say a point A located in first quadrant, you need to write the top view and the front view. And a point B located in second quadrant, you need to write the top view and the front view. Then a point A located in the third quadrant, then in the fourth quadrant. So you will be dealing with all the 4 quadrants, point located in all the 4 quadrants in the case of projections of points. But from projections of lines onwards, that is from projections of lines, projections of planes and projections of solid, the discussion is restricted to first quadrant, a line located in first quadrant or situated in first quadrant. Similarly, a plane located in first quadrant. Similarly, solid located in first quadrant. So we will be dealing with the top view and the front view of a line, plane and solid in the first quadrant only. Therefore, since the restriction is limited to first quadrant, you need to write XY line first. XY line is the imaginary line which separates HP and VP. So the concept is clearly explained by Professor Harish. We need to tilt horizontal plane to convert 3D into 2D. To write in a piece of paper, we need to tilt the horizontal plane clockwise. So when you tilt the horizontal plane, the imaginary line separating the top view and the front view is called as XY line. It is an imaginary line. Then in the case of points, no need to write VP and HP because you will be dealing with all the 4 quadrants. But in the case of straight lines, since you are dealing with only in the first quadrant, in the first quadrant, VP comes above the XY line and HP comes below the XY line, something like this. Look at here. I will take the help of the quadrants, the first quadrant, second, third and the fourth quadrant. Say this is HP and this is VP. Okay, you need to tilt horizontal plane clockwise. When you tilt the horizontal plane clockwise, look at here, if a point located in first quadrant, our study on lines is first quadrant, only the first quadrant. So concentrate only the first quadrant. The front view of this point will be on VP like this. So it is above XY line. The top view will be tilted to below XY line. This will be the top view. So front view will be above XY line, top view will be below XY line. The horizontal plane, when you tilt the horizontal plane, it comes below XY line. So in the first quadrant, vertical plane remains above xy line, horizontal plane remains below xy line. This concept is already explained by Professor B. Harish while discussing projections of points. So you need to write xy line first, then VP and HP. Okay. So if you do not write xy line, VP and HP, you may lose marks. Okay. Then in today's session, I will be taking different cases of lines. A line parallel to both HP and VP, a line parallel to HP and perpendicular to VP, second case. The third case is a line perpendicular to HP and parallel to VP. Fourth one, a line parallel to HP and inclined to VP. Then fifth one, a line inclined to HP and parallel to VP. Then the last case, which is most important, on which you are going to solve the problem, is the sixth one, a line inclined to both HP and VP. So to discuss this one, you need the information of these 5 cases. Okay, so this is the basics for this one. You will be dealing with the problems on a line inclined to both the plane. Okay, so starting with the first one, as I said, a line is the shortest distance between the 2 points. Say for example, this is a line A and B. I will take this point as A and this point as B. I will keep like this line, and you need to consider the board as vertical plane, and the floor as the horizontal plane. You should imagine the board as vertical plane, and you should imagine the floor as horizontal plane. Okay. Now I am keeping the line like this, so it is parallel to both VP as well as HP. Now how you can define this is parallel? Look, the distance from this point to the horizontal plane and the distance from this point to the horizontal plane, if it is same, the distance of this point to horizontal plane and this point to horizontal plane is same, then it is parallel to that particular plane. Then the distance from this point to vertical plane and this point to vertical plane, if it is same, then it is parallel. Okay, so this is parallel to both the plane. That is what I have written here. When it is parallel, you just project it. Projection means it is a beam of light passing from your eyes or eye of the viewer. It captures the point and it will take that particular point and it will project onto the screen or onto the plane. That is what the projection. So a beam of light, and here you need to use multiple light source. It is orthographic projection. In the orthographic projections, you need to use multiple light source. In the case of oblique projection, you need to use only one light source, as in the case of cinema theater. So here you need to use multiple light source. First light source from the eye of the observer captures this point and it will take this particular point onto the board. It will be located here, A dash, front view, it is written as A dash. Then the second point, a light source from the eye of an observer captures this point and it will project it onto the board or to the plane, this. So you will get 2 points, join those 2 points, you will get a line. So this is the projection of line in the front view. Similarly, shift the observer. So top, I will be looking like this. So when I am looking like this, the light source falling on this particular point captures the point and it will project it onto the ground, that is horizontal plane. There you will get A. Then B, point B, the projection light source captures point B and it will project it to the horizontal plane, that is point B. Okay, if you join these two, you will get the top view. So this is the top view and this is the front view, when a line parallel to both the plane. Then coming to the second one, a line parallel to HP and perpendicular to VP. So I will hold like this. In this position, look, this is flat. The distance from this point to ground and this point to ground is same. So it is parallel to HP and perpendicular to VP. Look, in the front view you can only see the point. You cannot see the line. You can only see the point. So it is perpendicular to VP and it is parallel to HP. This is also parallel to HP. This is also parallel to HP. Here I am not varying the distance from with respect to the horizontal plane like this. So this is parallel to HP, again this is also parallel to HP. I am not changing the distance. Okay. So this is the position perpendicular to the board, that is VP, and parallel to the horizontal plane. So now you just imagine the views, front view and the top view. So in the front view you can able to view only a point. Okay, you just locate it here, a point. Now you need to name it. If you give this as A and this as B, A and B, since A is visible, B is not visible because B is in line with A. B is in line with A, or B is behind A. Since B point is behind B is invisible, A is visible. Since B is invisible, I am going to put it in bracket. Okay, this is the convention used to represent a invisible point. If a point is in bracket, then it is invisible. It is understood that it is invisible. So A dash and B dash in the front view. Then top view I will be looking at like this. So the light source from my eye captures this point and it will project onto the horizontal plane. Then light source captures this point and project it to the horizontal plane, and if you join that point and if you tilt it, you will get like this, A and B. Look at here, here A is here, B is here. So this will be the observer view where A will be visible, B, since it is behind A, it is not visible. So this is the second case. Now the third case is a line perpendicular to HP and parallel to VP. So this is the position. In this position it is perpendicular to the horizontal plane like this and parallel to VP. The distance from this point to VP and this point to VP is same. So it is parallel to VP and it is perpendicular to the horizontal plane HP. Now try to imagine the views. Try to imagine the views, top view as well as the front view. If I have a look at from the top view, I can only able to see this point, a single point, because both the points are in line. Okay, this point. So in the top view, you can only able to see this one. So A is visible, B is invisible. When I am looking like this point is visible, this is not visible. So B, I will put it in bracket, which is invisible. Similarly, this one, if you look it from the front, the light source captures this point and projects here. Then the light source, one more light source captures this point and projects here. If you join those two, you will get the front view. Okay, so these two are opposite in nature. Similarly, the next case, a line parallel to HP and inclined to VP. Parallel to HP and inclined to VP. So I will start with the first case. The first case is parallel to both the plane. So this is the case first, parallel to both the plane. Now this case is parallel to HP and inclined to VP. So parallel to HP, I will not vary the distance, this one and this one. Instead I will vary the distance from this point to the board and this point to the board. I will keep this as constant, left hand side, this as constant, this as radius. I will going to rotate this like this. If I rotate this, then I am varying the distance of this point with respect to VP. Okay. Now in this position, the distance from this point to the board or the VP and this point to the board or the VP is different. Therefore, it is said to be inclined to VP or vertical plane. Now the distance from this point to the horizontal plane and this point to the horizontal plane is unchanged, same, therefore it is parallel to HP. So in this case it is parallel to HP and inclined to VP. That is what written here. You just imagine this particular case and need to imagine the views, the front view and the top view. Look at the front view, this point will be projected here and this point will be projected here, and of course in the front view it appears as a straight line only. Okay, you just project the point, front view, this point it comes here and this point comes here. If you join, it appears straight line. Now if you view in the top view, you just capture this point and throw it on the horizontal plane, capture this point, throw it on the horizontal plane. If you join, you will get like this, projection like this. So this is a line parallel to HP and inclined to VP. Then the next case is a line inclined to HP and parallel to VP. So inclined to HP, again I will start with the first case. The first case is line parallel to both the plane. This is the line parallel to both the plane. Now inclined to HP and parallel to VP. So the distance from this point to VP and this point to VP I will not change. Instead I will rotate this with respect to this point. With respect to this point I will rotate this like this. So in this case the distance from this point to the horizontal plane and this point to the horizontal plane is not the same. Therefore it is said to be inclined to HP like this. It is inclined to HP with some inclination. Okay, and since I have not changed the distance from this point to the vertical plane and this point to the vertical plane, it remains parallel to VP. So this is the position parallel to VP, inclined to HP, this one. Now try to, okay, I can also do it like this. I will keep this point, I will keep this point constant and I will lift this point up. So this is inclined to HP and parallel to VP because I need to get this one. Okay. Now try to project this point onto the board, point A, and try to project this point onto the board, point B, and join it. You will get this one. Similarly, top view, try to project this point onto the horizontal plane and this point onto the horizontal plane, and if you join it, it will be appears parallel. So if you look it in this view, it will be appears parallel. It will be straight line, appears straight line, appearing straight line. Okay, maybe this is nearer, this is far, but it appears straight in the top view if I look it in this view. Okay, so this is the fifth condition. Fine. So from these two, the fourth one and the fifth one, from these two I can extract some of the key points. So what are all those key points? You just observe this. If you just observe this, this is of its true length. This is of its true length, the entire length. And also if I just look at this, this is in its true length. Okay. So if I hold the line like this, the viewer from this point can able to see the entire length of the line. So projecting this point and joining will gives the true length of the line. So this is the true length of the line. But look at the length here and the length here. It is inclined position, this one, and this one is not the same. Okay, so if you tilt this and if you convert this inclination, if you take out the inclination with respect to horizontal plane, if you do it like this, if you rotate this line something like this, then this will be parallel to HP. That means if you take out the inclination with respect to HP, you will get it like this. So in the length of the line, true length of the line should be this one. This will be the true length, but in the top view, the length is shortened. It should be something like this amount, but in the top it will be shortened. Why it is shortened? Because of the inclination. Because of the inclination, you will not get the original length. So in this position, it is parallel to HP. In this position, you will get the original length. But in this position, look at here. This is rotating. That means it is having a curve here. Curve means it will be shortening like this. Okay. So this shortened length is called as apparent length. This shortened length is called as apparent length, whereas this length is called as true length. Similarly here, this is called as true length and this is called as apparent length. Okay. So from this concept, I can quote a key statement that if a line appears parallel, to xy line in one of the plane, then you will get the true length of the line in the other plane. I repeat, if a line appears parallel to xy line in one of the plane, then you will get the true length of that in the other plane. That is what the key statement I can extract from these two cases. This is very important. Okay, you need to memorize this every time when you solve the lines problem. If a line appears straight, look at here, a dash b dash is appearing straight. It is not exactly straight, it is just appearing straight in the view. Okay, similarly this AB is not exactly straight because it is this is the case, it is not straight if you look it from the top view. And here a dash b dash, it is not straight when you look it from the front view. It is not straight, but it is appearing straight. Okay, so if a line appears straight with respect to xy line, so if I talk with respect to xy line, then it is two-dimensional. Okay, if a line appears straight line to xy, then the true length of that particular line can be get in the other plane. This is what the concept I can extract using fourth and fifth case. Okay, so using this concept, we'll extend our discussion on the sixth case, that is a line inclined to both HP and VP, which is most important. Okay, so this is the fourth case, line parallel to HP and inclined to VP, and this is the fifth case, line inclined to HP and parallel to VP. So we know that this is the true length of the line and this is the apparent length of the line, whereas this is the true length, apparent length of the line, and this is the true length of the line. So from these two, the case 4 and 5, we can get a statement that you can put it as note: if a line appears parallel with xy line in one of the plane, then the true length of the line is measured in the other plane. You just observe these two figures. In these two figures, a dash b dash is appearing parallel to xy line. This is parallel to xy line, appearing parallel. This is not actually parallel because this is the case of a line parallel to HP. This is parallel to HP, inclined to VP. This is inclined to VP. So the distance from this point to the board and that point to the board is not same. It is inclined to VP. But in the front view, if you just have a look at from the front view, it will appear parallel because you need to project this point onto the board and this point onto the board, and then you are going to join those two points. So it will appear parallel to VP, but in the top view you will get the true length. So if a line appears parallel, in one of the plane, then you will get the true length of other in other plane. Then you will get the true length of other in that line in other plane. This is what the concept you can extract from these two. This is very important. Line appears parallel with a xy line in one of the plane, then its true length of the line can be measured in another plane. Okay. Now just club these two. I am going to combine the fourth case as well as the fifth case. This is what the figure I will get. Here the yellow lines is the case 4 where line is parallel to HP and inclined to VP. Then the green line is the fifth case, line inclined to HP and parallel to VP. Look at here. I am just clubbing these two to get the sixth case. The sixth case is line inclined to both the plane. When a line inclined to both the plane, it will be something like this. So this is parallel to both the plane now. I will giving the inclination with respect to VP as well as I am giving the inclination with respect to HP like this. Okay, this is the line inclined to both the plane. If you want to write the views, top view and front view of this particular line, you need to take the help of this one. So combining these two. So if a line inclined to both the plane, you need to reduce the condition with respect to both the plane, inclination with respect to both the plane, you need to reduce to either this or the two. Okay. So if a line is inclined to both the plane like this, in this case it is parallel to both the plane, I am giving the inclination with respect to VP, Now I will gain the inclination with respect to HP. So this is inclined to both the plane. So in this condition you will not get true length in the top view as well as in the front view, because it is inclined to both the plane. Okay, since it is inclined to both the plane, you will not get the true length. To get the true length, you need to reduce this particular condition to either this or this. Now I am just taking off the inclination with respect to VP. So I am just taking off the inclination with respect to VP. I am just rotating this with the radius equal to the length of the line, and center as this point. I am just rotating this line. So I am making this parallel to VP. So I am making this parallel to VP and inclined to HP. Okay. So this is the case of this one, line inclined to HP and parallel to VP. So this is written here with the green ink. So this is the true length of the line, and this is the top view apparent length of the line. So this you will get it once you take off the inclination with respect to VP. So that is how you need to convert the inclination from both the plane to any one of the standard case, either 4 or 5. Similarly, this is inclined to both the plane. Now I will taking off the inclination with respect to HP, something like this, HP. I have made this line parallel to HP now. This is parallel to HP and it is inclined to VP. So this case is the fourth case, line parallel to HP and inclined to VP, where you will get the yellow lines like this, something like this, where this is the true length. You will get it in the top view. So whatever you write below XY line will be the top view, whatever you write above XY line will be the front view, because we will be dealing with the first quadrant. In the first quadrant, top view falls below XY line and the front view above XY line. Okay. So now from the line inclined to both the plane, I have taken off the inclination with respect to HP, thereby making this line parallel to HP and inclined to VP. The fourth condition, fourth case, here I can get the true length and the apparent length. Okay, so this is the concept. Just rotate the line, take off the inclination, reduce to either fourth case or fifth case, get the views. Fine. Now here what I have done? I have taken off the inclination to make it parallel. That means to say, if this is parallel, A dash B dash, if this is parallel, earlier it was inclined. I have make it parallel, right? So earlier it was inclined. I need to draw a curve. Fine. So I have drawing a curve like this, and it should fall in the same locus, with the same locus, because if you just observe this point, if you draw a curve, the radius is not going to change. The radius of the line is not going to change. So it should be at the same locus. Or you can observe here this point. If you draw the curve, that curve from the front view, it will look like a line. This curve. Okay. If you draw like this, a curve in the front view, it will just look like a straight line. That is what this one, this straight line. This is actually in the top view it will be circle, but in the front view it look like a line. Okay. So you will get this particular point. That will be the true length, that will be the apparent length of this particular line. Okay. This will be the apparent length of this particular line, whereas this is the true length. Fine. So now I will rub off this one. I will write here B1 dash. B1 dash. Similarly, I will come to this one. Again, I can erase this. Not erase. I will just reduce the thickness. Again, if I come to this particular point, this line, the green line, which is inclined to HP and parallel to VP. Okay. It is inclined to HP and parallel to VP. So I will start with a line inclined to both the plane. This is the line inclined to both the plane. It is inclined with VP as well as inclined with HP. Now I will take off the inclination with respect to VP. I will take off the inclination with respect to VP. Okay. So from this condition, I will convert this condition into one of the case, either 4 or 5. Now I am taking off inclination with respect to VP like this. Now it is parallel to VP, inclined to HP. Parallel to VP and inclined to HP. So parallel to VP and inclined to HP is the fifth case. That is what written here. It is inclined to HP and parallel to VP. This is the true length and this is the apparent length. Why true length? Because you can it is parallel to VP, you can get the true length. Since it is not parallel to HP, in the top view it appears parallel. It appears parallel to XY line. Okay, so I have just taken off the inclination like this and I made it parallel, that is this one. So if I want this particular condition, again I need to rotate this. I am rotating it to make it parallel and again I am rotating back to make it inclined. Rotating it to make it parallel to VP and rotating it to make it inclined to VP. That is what I am doing. Okay, if you rotate this to make it parallel to VP, you will get this. If you rotate this, okay, make it parallel, make it inclined to VP, then you will get this one. Rotate this, make it parallel, make it inclined to VP, you will get this point. Now if you join these 2 points, this will be the true length, sorry, this will be the apparent length of the line. This is the true length of the line, this is the apparent length of the line. Okay, or else this is the true length, this is the apparent length, this is the true length and this is the apparent length. Fine. Now I can reduce the thickness now because it is not representing the line. This is just a construction line after tilting. Now for the confirmation, you just drop a line from B dash to, okay, this point can be called as B2 dash. If you drop a line from B1 dash to B dash, B2 dash, this should be with the same line. B1 dash as well as B2 dash should be fall in the same line. And the distance from the projector of A dash and distance from the projector of B1 dash, B2 dash is called as distance between end projector. Distance between end projector. Okay. So this is the complete solution. So you will arrive at the solution something like this once you solve the problem. This is just the introduction. So if you write the angles now, the angle measuring the apparent length here, A dash B1 dash is the apparent length in the front view, A dash B dash or B1 dash, A dash B1 dash is the true length in the front view. Similarly, A B is the true length in the top view, A B2 dash is the apparent length in the top view. So if you measure the angle of apparent length in the front view, it will be called as phi. Then if you measure the inclination with respect to XY line from the top view, the true length, then it will be theta. Then here from the XY line horizontal, if you measure inclination up to the apparent length, it is called as beta. Then the inclination here, this is not called as phi, this is called as alpha. This inclination is called as phi. Okay, so alpha is the apparent inclination in the front view, beta is the apparent inclination in the top view, theta is the true inclination in the front view, phi is the true inclination in the top view. Fine. Similarly, A dash B1 dash apparent length in the front view, A dash B1 dash is the true length in the front view, A B2 dash is the apparent length in the top view, A B1 is the AB is the true length in the top view. Okay. So this is what the case. If you just observe the figure, you will get some data like the distance of point A from horizontal plane. Similarly, distance of point A in front of horizontal plane. Since we are dealing with only the first quadrant, we need to refer point A above HP and in front of VP, since it is in the first quadrant, above HP and in front of VP. So this is above HP, this is in front of VP. Similarly, this point above HP, in front of VP. Okay, so I can have the distances of A and B with respect to HP and VP for parameters. Then inclination alpha, theta, beta and phi is the angle, apparent and true inclination in both front view as well as in the top view. Then the length, apparent length in the top view, front view, apparent length in the top view, true length in the front view, true length in the top view. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and distance between end projector 11. There are total 11 datas you can extract from this figure. So to solve a particular problem, you need to have minimum 5 datas to solve completely a problem online.